Week 9 distribution of the sample mean and distribution of the sample proportion. In this video, I will discuss the distribution of the sample mean. Our learning objectives are going to be describing the distribution of the sample mean, the normal population, and describe the distribution of the sample mean with non-normal population. Statistics such as the sample mean, x bar, are random variables since their values varies from one sample to another. As such, they have probability distribution associated with them. In this chapter, we're going to focus on the shape, center, and spread of statistics such as the sample mean. The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample size n. The sampling distribution of the sample mean x bar is the probability distribution of all possible values of the random variable x bar computed from a sample size n, from a population with a mean mu and a standard deviation sigma. The first step in creating the distribution of the sample mean is to obtain a simple random sample of size n. And then we're going to compute the sample mean. And then, assuming that we are sampling from a finite population, we repeat step 1 and 2 until all distinct simple random samples of size n have been obtained, which means we're done sampling the entire population and we're done computing the sample mean for each of these samples of size n. Let's say we have this specific example. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. Approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n is equal to 5 pennies from this population. So, the data on the following slides is going to represent the sample means for 200 simple random samples of size 5, n is equal to 5. For example, the first sample, n is equal to 5, has the following data: 2.433, 2.466, 2.423, 2.442, 2.456, and the mean is, or the sample mean for that specific sample is 2.444. So we're going to try to take samples of size 5, 200 samples of size 5, and for each of these samples we're going to compute the sample mean x bar. So here are the data. Now, if we collect all of the sample means from the 200 sample and we find the population mean, it is going to be 2.46, and this is similar to the mean that we obtain from the 200 samples. So if you take the sample means from the 200 samples that we just processed, it is going to be similar to the population mean. The standard deviation from the sample means, so if we take the standard deviation of the 200 samples of sample means of x bar, it is going to be 0.0086, which is smaller than the standard deviation of the population. So if you compute the standard deviation of the population of the weights of the minted pennies, then you're going to get a number that is slightly bigger than that. In the next slides, we will discuss the shape of the distribution. So this slide right here, for example, represents the histogram for the 200 sample means. So this represents the sample mean distribution, which means we collected all of the sample means and then we created this graph. So this is the graph, which is, it shows that it's bell-shaped or normally distributed. So now we know that because the original population that we studied, which is the population of pennies minted before 1982, was normally distributed, we know that the sample mean, the distribution of sample means that resulted from that, was also normally distributed. What role does n, which is a sample size, plays in the standard deviation of the distribution of the sample mean? So we notice if you could repeat that process many times and increase the size of sample, the standard deviation of the distribution of the sample mean decreases as well, which means as the size of the sample increases, the standard deviation decreases. So let's look at this example to understand the impact of size on a sampling variability. So we want to approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n is equal to 20 from the population of weights of pennies minted after 1982. The mean of that population was 2.46 and the standard deviation was 0.02 grams. So if we obtain samples now of size 20 and then compute all of the sample means, and then for that distribution of sample means we compute the mean and the standard deviation, you're going to notice that we still have the same mean. However, the standard deviation is slightly smaller now. It is 0.0045 compared to a sample size 5 that was 0.0086. So as we increase the size of the samples, we notice that the standard deviation decreases, which means the variability decreases as well. The shape is still normally distributed. So we can come up with a formula to compute the mean of the sample means and the standard deviation of the sample means. By computing the mean of the sample means and the standard deviation of the sample means, we're basically creating the sampling distribution of the sample mean. So we noticed from our observation that the mean of the sample mean is equal to the population mean. And we noticed that the standard deviation of the sample means is less than the population mean. Specifically, it is the population mean divided by the square root of the sample size. So we can also call the standard deviation of the sampling distribution, we call it the standard error as well. So sigma sub x bar is also known as the standard error of the mean. So we can basically understand that if a random sample x is normally distributed, the sampling distribution of the sample mean x bar is also normally distributed. Let's look at this example. We're trying here to describe in the distribution of the sample mean. In other words, we need to compute the mean and the standard deviation. So each time you're asked to describe the distribution of the sample mean, all you need to do is to find the mean and the standard deviation of that distribution. Here is an example. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. What is the probability that is the simple random sample of 10 pennies minted after 1982? We obtained a sample mean of at least 2.465. So to answer that question, first we need to find the mean and the standard deviation for the distribution of sample mean of that sample. Notice how the question is asking, what is the probability that in a simple random sample of 10 pennies, so the first characteristic here is to give you a sample size. That's how you know that you're not supposed to work with the regular normal distribution and you need to work with the distribution of the sample mean. And then the rest of the question is asking, and you have some keywords here. What is the probability in a simple random sample of 10 pennies minted after 1982? We obtain a sample mean of at least 2.465. In other words, that is the probability that we need to compute. We need to compute that in a sample of size 10, what is the probability that we're going to obtain a sample mean of at least means greater than or equal to. But since this is a continuous variable, it really doesn't matter whether you include the equal to or not. 2.465. In order to compute that probability, we need to know the mean of the sample means, because we're working with a sample here, we're not working with a single individual from the entire population. We're working with the sample mean from a sample of size 10. And also we need to compute sigma sub x bar, or the standard error for the mean. So in order to do that, we know that the population mean, or the mean of sample means, the mean of sample means is the same as the population mean, and that is equal to 2.46. And then the standard error for the means, or the standard deviation of sample means, is equal to the population standard deviation divided by the square root of the sample size, which is 10 in our case. So here is the formula that we used. And we obtain an answer of 0.063. Notice how this is smaller than the original standard deviation, which indicates that we're in the right direction. Now, just like what we did before, we have to standardize the given number. So we needed to find the probability that x bar is greater than or equal to 2.465. We need to standardize this number. So to standardize this number, we need to compute the z-score, that is the number x minus the mean divided by the standard deviation, and the z-score for that number is 0.79. Now, in order to find that probability, now it is equivalent to the probability that the z-score is greater than 0.79, since we standardized that. So we need to compute this probability, which we know if you try to graph it, it is the blue graph that you see here, and it is the blue area. In order to obtain the area to the right, we take 1 minus the area to the left. So we know that right area is equal to 1 minus left. And that is exactly what we do here. So in other words, it is equal to 1 minus the probability that z is less than 0.79. So if you plug that into Excel, you will get 1 minus 0.7852, which is going to give you 0.2148. And this is approximate because it's rounded to 4 decimals. Remember, we try to round our answers to 2 decimals all the time.